Hello everybody, and welcome to Chemistry 103. Today we're going to be discussing gases. We have just finished discussing chemical reactions and chemical equations, and also the various quantitative methods that we can use to describe these equations, and also the reactions that they describe. After we cover gases, we're also going to cover solutions, at least the basics of solutions, and then next time we're going to cover the quantitative predictions that you can make about solutions and how they relate to the next topic, which is chemical reaction rates and equilibrium. The topics that we're going to cover today will be essential for the understanding of that topic and also the topics to follow. Today will be the largest amount of information that you have to consume at once for the rest of the semester, and we should hopefully coast into the end of the summer session relatively easily. Keep an eye out for the second exam, which will be posted this week. You'll have a week to do it. It'll cover chapters 5 through 8. Alright, so beginning. Gases are compounds or elements that exist with large separation between them and that fill the container that contains them. Our atmosphere is a mixture of gases that are held onto the surface by gravity. It consists of 21% oxygen and 78% nitrogen, and then 1% other gases. There are other commonly used gases such as chlorine, which is used to purify drinking water. You may have heard of acetylene, which is used in welding and in torches. And then there are various semiconductor gases that are used such as hydrogen chloride and hydrogen bromide gas that have electrical properties that are useful. So a gas is a substance that is normally in the gas state at ordinary temperature and pressure, such as oxygen gas. This is distinct from a vapor, which is the gaseous form of a substance that is not a gas at normal temperature and pressure, but rather a liquid or a solid. This distinguishes the concept of, say, boiling water versus humidity. Boiling water has water vapor that comes off of it, and humidity is gaseous water that exists naturally in the air at normal pressure and temperature. There are 11 elements that exist in the gas phase: the diatomic molecules, hydrogen, nitrogen, oxygen, fluorine, and chlorine, and then the noble gases. The properties of gases include the fact that gases have no definite shape or volume, and they completely can fill their container. Gases can also be compressed to a smaller volume or expanded to a larger volume without changing the properties of the gas. And in general, we describe the behavior of gases with simple quantitative relationships referred to as gas laws. Now, the gas laws are called the gas laws because they describe the behavior of gases. They don't describe the behavior of solids or liquids. We have different equations for those. And these laws provide a mathematical link between measurements that we make and the chemical nature of the atoms or molecules in the gas. Gases behave fairly predictably, and we can start to relate their behavior to things such as temperature, volume, and pressure. So this theory that we use to describe the behavior of gases is referred to as kinetic molecular theory. And this is a mathematical model that explains the behavior of gases in terms of what we call an ideal gas. So an ideal gas would exist in somewhat of a fictitious state, or rather it is an ideal that all gases approach but never exactly reach, but it's a very useful point of departure because it basically describes the behavior of all gases. So in a gas, molecules are flying around at great speed with great separation between them, and from this model we can start to build a physical picture and understanding of the concepts of pressure and temperature at a molecular level. So as we know, gases are made up of tiny particles such as atoms or molecules, which are widely separated from one another, and they are in constant rapid motion. These particles in general have no attraction or repulsion for one another because they are neutral. And the particles of the gas are extremely small compared to the total volume which contains them. And therefore, a gas is mostly empty space. This is different from a solid or a liquid, where the particles are tightly packed together and therefore interact with one another. So this is a picture to help describe kinetic molecular theory. You have a box, in this case a rectangular prism, with a number of particles bouncing around inside of it off of the interior walls. This allows us to imagine the idea of the average kinetic energy of motion of gas particles. The way that we measure temperature is basically as a measure of the kinetic energy. Because particles are in constant random straight line motion, they collide with each other and the container walls at a fairly rapid rate, and the frequency determines the pressure. So these gas laws that I mentioned are generalizations that describe mathematically the relationships of four properties. Pressure, which is the force exerted by particles on the interior walls of a container. Volume, which is the amount of space that the container takes up. Temperature, which is a measure of the average kinetic energy of the particles. And then, of course, the amount of gas in moles. So pressure. Gas exerts pressure as its molecules collide with the surface of the container. So you can imagine any particle, be it a piece of sand or a rock, if you throw it at a wall, it will hit the wall with force and it will probably bounce off. The pressure is defined as the force per unit of area, or force divided by area. The atmosphere exerts pressure on the Earth by collisions of molecules with every surface it contacts. The reason that our atmosphere doesn't just fly away from Earth is that the particles have mass and are held to the surface by gravity. We measure gas using a device called a barometer, and this measures the height of the measurement is precisely a measurement of the height of mercury in a glass tube. This was invented in 1643 by a man named Torricelli, and the units are listed as millimeters of mercury. This is also known as a torr and is one of the three common units of pressure. It was the first unit of pressure because the first measurement of pressure that we had was the mercury barometer. However, now we have other units that are more fundamental, such as the atmosphere, which is, as you may have imagined, one Earth atmosphere, and this is equal to 760 torr, or 760 millimeters of mercury. And then the Pascal, which is an SI unit defined as a Newton per meter, is there are 101,325 pascals in one atmosphere. So more about the barometer. Here we see an evacuated glass tube that is inverted inside of a bowl of liquid mercury. When the evacuated glass tube encounters the liquid at atmospheric pressure, some of the liquid is sucked up into the vacuum, and it comes to a stop when the pressure of the pressure caused by the weight of the mercury that is risen up from the bowl is equal to the pressure of the atmosphere outside of the bowl. So the atmosphere presses down on the mercury and lifts it into the glass tube. And at sea level, where we get the 760 millimeters, is that in a barometer such as this, at sea level, the mercury is precisely 760 millimeters above the surface of the bowl. Pressure depends on the collisions of gas molecules with the walls of a container, and this further depends on both the number of collisions and the average force of the collisions. So you can imagine if there are more particles present, the number of collisions will be higher, and the faster the particles are moving, or aka the higher the temperature, the larger the pressure will be, because the average force will be larger. So I mentioned that atmospheric pressure is caused by air being pulled towards Earth by gravity. Now, the atmospheric pressure can change based on the weather. And here it says weather can change the pressure, but in reality, it's pressure changes that change the weather. So you've probably heard of high pressure centers and low pressure centers. If you have a lot of evaporation of water in one area, for instance, because it's really hot, that water will go into the atmosphere. It will increase the overall pressure, and that will cause the air in that area region to move away to equilibrate the pressure and make it go lower. And this will cause the water vapor that has just evaporated to move away as well. And if there is dry air nearby, there may be a mixing that causes precipitation. Other things that can change pressure are altitude. So the higher up from sea level you go, the less gravitational pull there is, and this causes the air to be thinner. Another property we talked about with gases is volume. Volume depends on the pressure of the gas. It also depends on the temperature of the gas, and it depends on the number of moles of gas. And we express volume in milliliters or liters. Temperature, as I said before, is related to the kinetic energy of the molecule, which is in turn related to the velocity of gas particles. The velocity of gas particles increases as the temperature increases. Another important thing to remember is that when dealing with gas law problems and calculations, you always use temperature expressed in kelvins, because Celsius degrees don't exactly account for the proportionality listed in the gas laws. Amount of gas is the number of moles, and the properties of a gas, the other properties of a gas, volume, temperature, and pressure, are related to the amount of gas present. We measure gases in grams because it's usually convenient to weigh things, and it's significantly more convenient to weigh things than count particles. However, once you have the mass, you have to convert it into moles, because the gas law calculations require that, because the properties are dependent on number of particles rather than mass of particles. So we always convert mass in grams to moles when we're doing calculations. So the first relationship we're going to discuss is the relationship between pressure and volume, discovered by Boyle. When we hold T and N constant, temperature and number of particles, then the pressure on the gas increases proportionally with as the volume decreases. So as you decrease the volume, there are more collisions with the walls, which increases the pressure, because there's less total space available for the gas to move. So more about Boyle's law. On the right here, we have a pictorial representation of Boyle's law. We have a piston and a cylinder. And the first is a volume of 4 liters and a pressure of 1 atmosphere. And if we compress the volume to 2 liters, the pressure increases to 2 atmospheres. Now, Boyle determined this from observations, not kinetic molecular theory. And in this case, it's important that only pressure and volume are allowed to change. So sometimes when you compress a gas, the temperature will go up. However, in this case, the gas is in contact with basically the environment, so it cools as it is compressed, which keeps the temperature constant. There is an inverse relationship between P and V, which means P is inversely proportional to V, and that means that the product P times V is equal to a constant K. Additionally, because the product of P and V is equal to a constant, if you have a closed system and you have it at an initial pressure and an initial volume, then if you change the pressure, the volume will change accordingly. That is what's shown here in this piston. So the first pressure is 1 atmosphere, the first volume is 4 liters, and PV is sent as constant. The first pressure volume product will be equal to the second pressure volume product. And as you can see, 4 times 1 equals 4, and 2 times 2 equals 4. The second relationship we're going to discuss is the relationship between temperature and volume. So a man named Charles found out that the volume of any gas will increase with an increase in temperature. More precisely, the volume of a sample of gas is directly proportional to its temperature in Kelvin. And this holds as long as the pressure and number of particles are held constant. So, Charles' law tells us what happens when temperature increases. So when temperature increases, the speed of the particles increases, which increases the force with which they hit the walls. If the volume can change, then the force stretches out the container until it ends up with the same pressure it had before, just at a larger volume. So, here is a picture of this. Volume and temperature are proportional. So if pressure and the amount of gas are constant, as you increase the temperature, the volume will also increase. Here we see a piston again. We have the first temperature is 200 Kelvin, and the volume is 1 liter. We increase the temperature to 400 Kelvin, and the volume increases to 2 liters. This means this is V equals BT is another statement of the proportionality, B being the proportionality constant. And since we have two closed systems, the V1 divided by T1 will be equal to V2 divided by T2, because in this equation here, if you solve for B, you have V over T equals a constant, and so in a closed system, these two quantities have to be equal to one another. Now, this introduces the concept of absolute zero, because if we could cool a gas enough, its volume would reduce to zero. Absolute zero is 0 Kelvin. It is a theoretical temperature because at a low enough temperature, all gases liquefy, including helium. So in order to find absolute zero, you compress a gas and measure its temperature decrease, and at a certain point it will liquefy, but you have a straight line, so you just draw a straight line out from the volume and temperature curve, and it will intersect the x-axis at minus 273 degrees Celsius, which you will do in the gas lab. More about temperature and pressure. Moving on to temperature and pressure. A man named Gay-Lussac discovered the relationship between gas pressure and temperature. The pressure of a sample of gas at a constant volume is directly proportional to its temperature in Kelvin. So, again, as long as you keep the volume and the number of particles constant, this relationship will hold. So, by kinetic molecular theory, as the temperature increases, the speed of the gas molecules increase, which increases the frequency with which they hit the container walls, which increases the pressure, which is shown here. Again, it's our picture of the piston. And our relationships, again, P over T is a constant. And so if you have a set of pressures and temperatures for two closed systems that are related to one another, I'm sorry, one closed system with two different pressure and temperature values, the first pressure divided by the first temperature will be equal to the second pressure divided by the second temperature. Now, this brings us to the concept of vapor pressure and boiling point. So all liquids under real conditions are constantly evaporating. This is because molecules at the surface of the liquid will break away from the liquid and enter into the gas phase spontaneously. However, in a closed container, these gaseous molecules cannot escape to the atmosphere, and so they remain at equilibrium as a gas that exists above the liquid. And a pressure gauge attached to such a container will indicate a vapor pressure. Now, there is a certain point at which molecules will evaporate in this closed container. They will evaporate and condense at the same rate. This is known as saturated vapor pressure. And that means that the liquid to gas rate is equal to the gas to liquid rate. We call the vapor pressure the pressure exerted by its vapor at equilibrium. If you heat a liquid, its vapor pressure will increase, and the boiling point refers to the point at which the vapor pressure is equal to atmospheric pressure. This is why when you increase the altitude, the boiling point of liquids goes down, because atmospheric pressure is lower, and so the vapor pressure does not have to be as high to equal atmospheric pressure, and therefore reaches that temperature at a lower temperature. Now that we've talked about all the different gas laws, we are going to talk about something called the combined gas law, which takes into account Boyle's law, Charles' law, and the Gay-Lussac law. So the combined gas law states that the product of pressure and volume divided by temperature is equal to a constant, and therefore in a closed system, if you have initial pressure, volume, and temperature, and you change one of those quantities or two of those quantities, then the third quantity will adjust to retain the same constant value. This law applies to all gases and mixtures of gases, and if you know 5 of the variables, the 6th can be calculated. Now there's one more relationship we have to talk about before we can talk about the ideal gas law, and that is called the relationship proposed by Avogadro. Now, you probably remember Avogadro from his handy number that we use to define the mole. The way that he actually figured this number out was through the gas law that he discovered, which is the relationship between volume and the number of moles of a gas. So he discovered that equal volumes of two different gases at the same temperature and pressure will have the same number of molecules. And this seems a bit counterintuitive, but we will hash it out and hopefully it'll make sense to you. So, the volume of gas varies directly with the number of moles of gas as long as the pressure and temperature remain constant. Avogadro's law says that if you increase the number of moles, you increase the volume. And if you cut the number of moles in half, the volume will be cut in half as well. This is because more molecules push on each other and the walls, which stretch the container and make it larger until the pressure is the same as before. Here we see our piston with the volume proportional to N, or the volume being equal to a constant A times N, and then also the relationship V1 over N1 equals V2 over N2. If you solve for A in this equation, V over N equals a constant, and therefore in any closed system, an initial volume and number of moles has to be equal to a second volume and number of moles. So this brings us now to the ideal gas law. So we have four variables, P, T, V, and N, and we can relate them all to one another using the three different relationships concerning the volume of a gas. So the first one is Boyle's law, where you have N and T constant, V equals a constant times, or a constant divided by P. Second one is Charles' law, where you have N and P constant, and that states that the volume is equal to a constant times the temperature. And you have Avogadro's law, which says that the volume is equal to a constant times the number of moles when you have the pressure and temperature held constant. This allows us to combine them into a single expression that states that the volume is equal to a constant times the temperature times the number of particles divided by the pressure. We usually write this in such a way because it allows us to calculate properties of gases from scratch. Given three of the variables, you can calculate the fourth. In this case, R is a constant. PV equals nRT is something you've probably heard of before, maybe not, but it is one of the most important equations in science. R is referred to as the gas law constant, and it has two different units that are considered correct and widely used. The first one is R equals 8.314 joules per mole per Kelvin, which, as you can see, is in SI units. The joule is a SI unit of energy. However, many measurements of gases are taken in liters, and many volumes are in liters, and pressures are taken in atmospheres. And so there is also a gas law constant with the units of liters times atmospheres per mole per Kelvin. You can see this is a pressure times a volume, which makes logical sense considering what the gas law is. Notice that these numbers differ by 2 orders of magnitude, so if you mess up which one you're using, you will get the wrong answer. This is the one that we're going to use probably most often, simply because it's easier to measure things in liters and atmospheres than it is to measure in joules. So from the ideal gas law, you can rearrange it to make the various equations from Boyle's, Charles, or Avogadro's law. Boyle's law, if we have the temperature and number of moles constant, then the ideal gas law reduces to P1 V1 equals a constant, which is equal to P2 times V2. In this case, if N and T are constant and R is a constant, then nRT is a constant, which gives us P1 V1 equals P2 V2. Likewise, Charles' law can be deduced because the pressure and number of moles are constant. So V1 over T1 equals nR over P, which is a constant, which is equal to V2 over T2. And then Avogadro's law, where pressure and temperature are constant, we have V1 over N1 equals TR over P equals V2 over N2. And we get our proportionality relationships as well. Now that we've talked about the ideal gas law, we can introduce the concepts of standard temperature and pressure, or STP, and also the concept of molar volume. So gas volumes can only be compared at the same temperature and pressure. Otherwise, you have altered the properties of the system and the numbers won't make sense. Therefore, if you standardize temperature and pressure and report everything with relation to a temperature of 0 degrees Celsius and a pressure of 1 atmosphere, then when you quote a quantity at standard temperature and pressure, then you can be sure that it correlates to a different gas volume at standard temperature and pressure. And we'll go through this a little bit more. So 0 degrees Celsius, if you'll remember, is 273 Kelvin, and 1 atmosphere is 760 millimeters of mercury. This will be an important relationship to remember when you're doing unit conversions. So, molar volume. If you have 1 mole of a gas, any gas, at standard temperature and pressure, it will have a volume of 22.4 liters. And it doesn't matter what gas it is, this will always hold. This is known as the standard molar volume, and it was determined by Avogadro. When used in calculations at standard temperature and pressure, the conversion factors that are used are 1 mole of gas per 22.4 liters, or 22.4 liters per 1 mole of gas. So this means that 1 mole of helium will be 4 grams and will have the same volume as 1 mole of oxygen, which is 32 grams at 273 Kelvin in 1 atmosphere, which will be the same volume as 1 mole of nitrogen, which weighs 28 grams. So now you're starting to see the difference between gases. Obviously, the density of these gases will be different because they have the same volume but different masses. So we were talking about density. At standard temperature and pressure, the density of a gas depends on its molar mass. The higher the molar mass, the greater the density, and the greater the density, the more likely it is that a gas will sink below other gases. So, for instance, carbon dioxide has a higher molar mass than both nitrogen gas and oxygen gas, so it is more dense than air. This means that carbon dioxide will sink to the ground in air, which is why it is used in fire extinguishers, because not only does it not burn in a fire, it covers the fire and prevents O2 from reaching the combustible material because it sinks below the level of the air. By contrast, helium is less dense than air, which is why we fill balloons with it, because helium rises. So, at the same temperature and pressure, 1 mole of any gas will occupy the same volume. It's very important to remember this relationship. So, now we're going to use the ideal gas law to make predictions about the pressure, temperature, volume, or number of particles present in a gas. So, as I said before, if we know 3 of the 4 variables, we can calculate the 4th. In this case, if we know pressure, temperature, and number of moles, we can calculate the volume. And if we know these quantities, we can calculate the molar mass of a gas, which can then be used in stoichiometric calculations with chemical reactions. So, to begin, we have moles of gas A, and we want to get to moles of gas B. So, we start by determining the grams of A, because we can interchange them if we know the moles of A, and the molar mass, we can determine the grams. Likewise, if we know the moles of B, we can determine the grams of B and go back and forth between them. MM refers to the molar mass. Now, we can get to these from the pressure or the volume, provided we know the temperature. And we figured them out using PV equals nRT. So, in general, problems will be set up so that you are given a set of variables and one missing variable, and you will rearrange the equation to solve for the missing quantity. This requires some algebra. Hopefully you guys remember all that stuff. It's fairly simple though. So PV equals nRT. If we want to figure out the volume, we solve for volume by dividing by P. And we have then V equals nRT divided by P. So the step-by-step method for this, first we determine the initial values, and then we determine the final values. We set two equations equal to another, one for the initial values, one for the final values, and then we solve for the unknown variable. So first we're going to talk about the combined gas law, because it's a bit easier, and then we're going to go and talk more about the ideal gas law. So the combined gas law is the simple proportionality relationship, P1 V1 divided by T1 equals P2 V2 divided by T2. We want, say we want the initial temperature. So we would solve for T1 by multiplying by T1 and dividing by P2 V2 over T2, which puts P2 V2 in the denominator and T2 in the numerator. And now we're going to do some examples. So say we have a balloon with 1,300 moles of hydrogen gas. So this is at a temperature of 23 degrees Celsius, and the pressure is 750 millimeters of mercury. What is the volume of the balloon? So we start, we have our balloon, and it has 1,300 moles of hydrogen gas at 23 degrees Celsius and 750 millimeters of mercury, and we're looking for the volume. So first we convert our units to the appropriate units. We have our pressure in torr, and we have to convert to atmospheres, so we know that there are 760 torrs in an atmosphere. So if we multiply 750 times 1 over 760, we get 0.987 atmospheres. We don't need to convert moles, but we do need to convert temperature into Kelvin. So 23 plus 273 is equal to 296 Kelvin. And the appropriate gas constant is 0.082 liter atmospheres per mole Kelvin. So now we need the volume, which means we have our relationship V equals nRT over P. And we have all of those quantities given. So 1,300 moles times 0.082 liter atmospheres per mole Kelvin times 296 Kelvin divided by 0.987 atmospheres. The moles cancel, atmospheres cancel, and Kelvin cancel. So we're left with liters as the units, and there are 31,969.2 liters in this balloon. That means this balloon is about the size of a small swimming pool, so it might be like a weather balloon or something. Another example, say we have 0.105 grams of a gaseous compound that exists at a pressure of 561 millimeters of mercury and has a volume of 125 milliliters at 23 degrees Celsius. What is its molar mass? So, we know that PV equals nRT. We also are given the pressure, we're given the temperature, we're given the volume, and we're given the mass. So right off the bat, we have to do some conversions. 561 torr divided by 760 torr gives us 0.738 atmospheres. 23 degrees Celsius plus 273 degrees equals 296 Kelvin, and then 125 milliliters is equal to 0.125 liters. And we have our mass in grams. So, first, we set up, we have to find the number of moles. So we know the number of moles is equal to PV divided by RT, based on the ideal gas law. And since we are given the pressure and the volume and the temperature, and we have a gas constant, we can calculate 0.738 atmospheres times 0.125 liters divided by 0.082 liter atmospheres per mole Kelvin times 296 Kelvin gives us, after canceling units, 3.79 times 10 to the minus 3 mole. Now, we have a mass, and we know that the molecular weight, or the molar mass, is equal to the number of grams divided by the number of moles. And so we have 0.105 grams, and we have 3.79 times 10 to the minus 3 moles. And so this is equal to 27.66 grams per mole. Another example, gaseous ammonia is synthesized by the following reaction. We have nitrogen gas plus 3 hydrogen gases yields 2 ammonia gas molecules. So suppose you take 355 liters of hydrogen gas at 25 degrees Celsius and 542 millimeters of mercury and combine it with as much nitrogen gas as is required to react all of the hydrogen gas. How much ammonia do you produce in moles? And then, if this amount of ammonia is stored in a 125 liter tank at 25 degrees Celsius, what is the pressure of the gas? So here is a picture. We have hydrogen gas in a flask, and it is mixed with nitrogen and produces NH3. So our starting conditions, we have 355 liters, we have 25 degrees Celsius, and 542 torr. And our ending conditions are 125 liters and 25 degrees Celsius. So first we need to find the number of moles of ammonia created. And then in part 2, we need to find the pressure of that ammonia in the container supplied. So we begin with our stoichiometric calculation of finding the number of moles of hydrogen that's required to produce a mole of ammonia. We know that there are 760 torr in 1 atmosphere, and so 542 divided by 760 gives us 0.713 atmospheres. 355 liters is given, and then 25 plus 273 is 298 Kelvin. And we also know we're going to use the relationship N equals PV over RT. Given all those values, we calculate the quotient after canceling units. And we're left with 10.35 moles of hydrogen gas being consumed in this reaction. Now, we have a mole-mole factor to deal with. For every 3 moles of hydrogen gas, we produce 2 moles of ammonia gas. And therefore, we have the following proportionality relationships, which we can then use to convert moles of hydrogen into moles of ammonia. And so we have 10.35 moles of hydrogen gas times 2 moles of ammonia per 3 moles of hydrogen gas, which gives us 6.9 moles of ammonia produced in this reaction. Now that we have the number of moles of ammonia gas, we have to convert it to volume. And we know that, we have to convert it to pressure. So we have the temperature, which is 298 Kelvin again. We have the number of moles, which is equal to 6.9. And we have the volume, which is 125 liters. And so we have the ideal gas law, PV equals nRT, or in this case, P equals nRT over V. And we have all those values, 6.9 times 0.082 times 298 divided by 125 is equal to 1.35 atmospheres. So the pressure of this ammonia gas will be a little bit more than atmospheric pressure. All right, now we're going to do another example using Boyle's law. If you have carbon dioxide at a pressure of 55 millimeters of mercury in a volume of 125 milliliters, and then compress it so that the new pressure is 78 millimeters of mercury, what is the new volume of the gas, assuming the temperature does not change? So you have a balloon. It has a pressure of 55 torr and a volume of 125 milliliters. And you have a second balloon that has a pressure of 78 torr, and you want to know its new volume. Now this scenario is something where if you take a balloon and you put it into a box where the pressure is higher, you will exert a total pressure on the outside, which will be equal to the pressure inside the balloon. Obviously, that's the only way that you could compress a balloon in this fashion. So this example, we have a pressure, an initial pressure and an initial volume, and we have a final pressure, and we're looking for the final volume. So we do our conversions and using our P1 V1 equals P2 V2 relationship. We can solve for the second volume, P1 V1 divided by P2 equals V2. And then we don't even have to convert our units because they will cancel out. The millimeters of mercury in any case will cancel out, which leaves us with units of milliliters. 55 times 125 divided by 78 is equal to 88.14. Now we're going to play with Charles' law a bit. So say we have a balloon that has helium. It's inflated to a volume of 45 liters at room temperature. If it is then cooled to minus 10 degrees Celsius, what is the new volume, assuming the pressure the external pressure does not change? So we have our balloon, we have our initial temperature and our initial volume, and we have the same balloon shrunk at a new temperature and a new volume. So first we set up our givens and our needed quantities. So T1 is equal to 298 Kelvin. First volume is 45 liters, and the second temperature is 263 Kelvin. We know that V1 over T1 is equal to V2 over T2, and solving for V2, T2 times V1 over T1 is equal to V2. Plugging our values into this equation, 263 Kelvin times 45 liters divided by 298 Kelvin. Kelvins cancel, and we're left with 39.7 liters. Here is another example. Say you have a 22-liter cylinder of helium at a pressure of 150 atmospheres and 31 degrees Celsius. How many balloons can you fill? Each with the volume of 5 liters on a day when the atmospheric pressure is 755 milliliters of mercury and the temperature is 22 degrees Celsius. So this is going to require a bit of thought. You have a helium cylinder. You have an initial volume, pressure, and temperature. And then you have a number of balloons, each with a volume V2 and a pressure equal to atmospheric pressure, which is 755 torr, and a temperature equal to atmospheric temperature, which is 22 degrees Celsius. And we know that each balloon is 5 liters. So we start out with our givens. P1 is equal to 150 atmosphere, T1 is equal to 304 Kelvin, and V1 is equal to 22 liters. We can do our calculations here. In terms of P2, we're given 755 torr. To convert that to atmospheres, it's 0.99 atmospheres, and then our atmospheric temperature is 295 Kelvin. We're going to use the relationship PV over T equals NR because the number of moles is not changing. And we're also going to use the relationship P1V1 over T is equal to P2V2 over T2. Solving for the second volume, P1V1 times T2 over P2 times T1 is equal to V2. Now, with that, we have V2 is equal to 150 atmospheres times 22 liters times 295 Kelvin divided by 0.99 atmospheres divided by 304 Kelvin. Atmospheres cancel, Kelvins cancel, and we are left with a total volume possible of 3,234.6 liters. Now, we also know that each balloon wants to be filled to a capacity of 5 liters. And therefore, if we divide 3,234.6 by 5, we get 646.9 balloons. And since we can't have a fraction of a balloon, we'll say that it's 646 balloons. Next, we're going to talk about mixtures of gases. So most real gases are mixtures, such as the air we breathe, which is a mixture of nitrogen, oxygen, carbon dioxide, water vapor, and other gases like argon. Each of these gases exerts a pressure, and these pressures all add up to the total pressure, which is atmospheric pressure. Now, in this mixture, each molecule moves in the container independently of the others and collides with the container as frequently as if it were the only gas present. Which means that the partial pressure is the pressure exerted by an individual gas, which is equal to the pressure it would exert if it were alone under the same conditions. We describe this relationship using something called Dalton's law, which states that the total pressure for a mixture of gases is the sum of the partial pressures of the individual gases. Because each gas behaves independently of the others, this is because they're all ideal gases, which means they don't interact with one another. Obviously, in the case of real gases, there will be a slight amount of interaction. However, as long as the pressure and temperature are in the right range, so low pressure and high temperature, the gases will behave roughly ideally. So the total pressure exerted by the gas is related to the total number of moles of gases. And so if you increase the number of moles, the partial pressure will change. This is illustrated here. Say you have 2 tanks. You have a pressure of helium and at 2 atmospheres and a pressure of argon at 4 atmospheres. If you were to combine these 2 gases together directly in the same container, their pressure would be 2 atmospheres plus 4 atmospheres equals 6 atmospheres. So this is useful in situations such as filling a scuba tank. So say you have a scuba tank which contains oxygen gas at a pressure of 0.45 atmospheres, and it's mixed with helium at 855 torr. What is the total pressure in torr in the tank, assuming the volume and temperature are held constant? So first we write the equation for the sum of the partial pressures. So the total pressure is equal to the pressure of oxygen plus the pressure of helium. And then we rearrange the equation to solve for the unknown pressure and convert our units. So in this case, we have 0.45 atmospheres, and we want it to be converted to torr. So we know there are 760 torr in 1 atmosphere. Atmospheres cancel, and we have 0.45 atmospheres is equal to 342 torr. Now we can do our addition. So 342 torr plus 855 torr is equal to 1.2 times 10 to the 3 torr. All right, so now we're going to drive that home with another example. So for a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atmospheres. If the oxygen has a partial pressure of 1,280 torr, what is the partial pressure of the helium? We have 3 options: 520 torr, 2,040 torr, and 4,800 torr. So the way we work this out is we write the equation for partial pressure, which is the total pressure is equal to the sum of oxygen and helium pressures. And we rearrange and solve for the unknown pressure. So the pressure of helium is equal to the total pressure minus the pressure of oxygen. And we know the total pressure is 8 atmospheres. So we convert that to torr by multiplying by 760. And we're given 6,080 torr is equal to 8 atmospheres. Now, to solve for a pressure of helium, we take 6,080 torr and subtract 1,280 torr, and this gives us 4,800 torr, or 4.8 times 10 to the 3 torr, which means that the answer is C. And obviously, if the reason this is important is if you have a container of pure oxygen and you come up from the depth too quickly, it can cause your blood to bubble and give you something referred to as the bends, which disorients you and could cause you to have a fatal accident by diving too deeply and messing up the amount of oxygen dissolved in your blood. Now, there's another concept we're going to talk about here real quick. It's called the wet gas problem. So because water has a vapor pressure, any gas it comes in contact with will become mixed with water. So say you have an experiment where you have 352 milliliters of gaseous nitrogen, which is collected in a flask over water at a temperature of 24 degrees. The total pressure of the gases in the flask is 742 torr. And what mass of nitrogen is collected, assuming the vapor pressure of water is 22.4 torr. So this is a partial pressure problem. Here's our apparatus. You have a tube that pumps nitrogen through water, and the gas is collected in this flask. We know that the gas is a mixture of nitrogen and water. And we have a number of parameters that are given to us. The first one is the volume, which is 352 milliliters. We have the temperature, which is 24.0 degrees Celsius. We have the partial pressure of the water and the nitrogen, or rather we have the total pressure and the partial pressure of water. And we're looking for the mass of nitrogen, which requires us to calculate the number of moles of nitrogen, which requires us to calculate the partial pressure of nitrogen. So the way that we do this is by knowing that the partial pressure of nitrogen is equal to the total pressure minus the partial pressure of water. So 742 minus 22.4 torr, which is equal to 719.6 torr. And if you convert that to atmospheres by dividing by 760, you get 0.947 atmospheres. You also know that the volume is 352 milliliters, which is 0.352 liters. And the temperature is 24 degrees Celsius, which is equal to 297 Kelvin. Now that you have the pressure, the volume, and the temperature, you can determine the number of moles with N equals PV over RT. So 0.947 times 0.352 divided by 0.082 times 297 is equal to 0.0137 moles of nitrogen gas. And since we know the molar mass of nitrogen gas is 28.01 grams per mole, we can cancel the moles, multiply through to get 0.384 grams of nitrogen gas. Now that concludes our discussion of gases, and we are going to now move on to solutions.